And we're very excited to have Bill share some more recent thoughts. He said this was going to be a true rough cut, so that's exciting. Some new thoughts on the links between boreal peat, carbon storage, and climate. So please welcome Bill, and excited to hear what you have to say.
Okay, I haven't given this talk before, so I have a cheat sheet here and need to use my glasses. This is a notion that's come to mind the last year or two that falls out of the early anthropogenic hypothesis, but it's almost like an inversion kind of situation. And I avoided in my talk last night a bunch of complexities having to do with carbon budgets. If there were geochemists, certain number of geochemists in the audience last night, I would have been savagely attacked, but there weren't, so I wasn't. But this will address some of the issues that I skirted around, introduce some new information. So the title I've got is a question, which I think I can make a fairly convincing case that the answer to that is yes. And I've had the notion for a year or two, but I just haven't gotten the energy together to write a paper. So and this is the first time I've ever talked about it. So this is a good rough cut for a test case, first drive. Show you a figure that I used last night. Here's a CO2 record going back 400,000 years. And you'll notice that there are peaks in CO2 about every 100,000 years, after which the CO2 level drops. I don't think I need it. You can see after the peak values, CO2 comes down. And there's variation, some of which is orbital scale variation. So the question is, why does CO2 go down, or what's the cause of the whole cycle, actually? And if you go to the ocean, to the geochemistry, chemical oceanographer community, prevailing answer is that by the time you get to glacial maximum times, like 25,000 years ago, where the CO2 is down low, most of the carbon that was in the atmosphere during high CO2 times is in the deep ocean, and it's sequestered largely out of contact with the atmosphere. And then once you get into the deglaciations, these rapid rises of CO2, that's the deep ocean releasing carbon to the atmosphere. That's the current wisdom as far as I know it stands, and that's mostly coming out of chemical oceanographers in a variety of disciplines. And it's not a subject that I'm anywhere near expert on. The mechanisms they call on to get the carbon into the deep ocean, and so now I'm talking about the beginning of the drop of CO2 from these peaks, is that when in the modern ocean, there are two mechanisms. In the modern ocean circulation, you have the yellow showing North Atlantic deep water, which doesn't have much carbon sinking into the ocean, and the Antarctic bottom water, which has lots of carbon, which is in effect organic carbon or CO2 getting into the deep ocean. So in the modern ocean, there's storage of CO2 in the deep ocean. But at glacial maximum times, for various reasons, the sinking Antarctic bottom water green signal gets much more powerful, and it's thought to pull down just in the overturn of the circulation. It's thought to pull down carbon and store it in the deep sea. That's mechanism number one. Mechanism number two is that it's called the glacial carbon pump, and that is that photosynthesis occurs in the surface waters, of course, in the ocean, and in the process of photosynthesis, organic carbon sinks to the into the ocean, some of it makes it to the deep ocean. So if you have some mechanism that causes more sinking, there's some seats here if you like. If you have a mechanism that creates more sinking, you're going to get that carbon down there sequestered in the deep water. So those are the two mechanisms that get you to the situation of having CO2 start to go down after interglacial circulation times. And that would be the community's absolutely prevailing opinion right now. I got interested in peat burial for a reason that I avoided in my talk last night, but peat burial during the Holocene, and that led me into some thinking. There was a paper for which Klinger was first authored, that's 1996, the potential role of peatland dynamics in ice age initiation. And so his idea was that peat bogs, this is basically around the Arctic Ocean, can store lots and lots of carbon. And if you keep burying carbon in peat bogs around the Arctic Ocean, it's not going to be available to the atmosphere. So he was thinking maybe the hypothesis that I'm going to talk about was, it was an early suggestion. There were other complexities in what they suggested that were not well grounded. I should say Franzen was the major figure in this paper, although he was not first author. So it's real simple. CO2 starts to go down because you're burying organic carbon in peat, which is taking it away from the atmosphere. So this is showing up. There's a seat here. So I was coming at this from another point of view. In effect, I'm trying to figure out what is it that's canceling a particular geochemical signal that should show more terrestrial carbon release due to the kinds of data that I showed you last night that I'm going to show you again today. It shows up in some respects and it doesn't show up in other respects. So here's a map by Zaicheng Yu from Lehigh University showing the distribution of rain that it was canceled by anthropogenic emissions, almost coincidentally, almost the same amount. And Jed Kaplan's model provides estimates of the amount of terrestrial carbon released. So I've taken the red dots, which are the anthropogenic effect, and hollowed them out to remove them from consideration, because people were not a factor 100 or 200 or 400,000 years ago. Our species was present some ways back, but not farming. And so now just focus on the fact that peat burial takes large amounts of carbon out of the terrestrial vegetation atmosphere system, equivalent to tens of parts per million CO2, and buries it out of sight. And that in previous interglaciations, if that went on, it would certainly have driven a CO2 decrease, but there wouldn't have been any cancellation by people. So did peat burial initiate previous interglaciations when there weren't any human factors at work? And I say it seems to me like it would have to. And that's so simple I haven't had the courage to write it up and submit it for publication, but it makes good sense to me, and sometimes simple good sense is okay. So this is a test drive, so I'd be happy to have you jump this idea and thrash it out. Yeah.
I hope I could get you right here. Is the blue line on the middle the sum of the two other?
Is what?
Is it the sum of the two other, the top and bottom graph?
The basically what I'm saying that in this interglacial, the net release of terrestrial carbon is the sum of A and C. And initially, my hypothesis focused on C, that we're putting all this CO2, this terrestrial signature carbon in the atmosphere. But I got the criticism that it doesn't show up in this delta C13 CO2 signal, which is terrestrial carbon. There's a signal, but it's much too weak. And then I discovered, and this new research was coming in from Zai-Cheng Yu, that the peat burial was going on at an enormous rate. And so yes, the real story of the terrestrial carbon signal is the combination of human emissions and peat burial, the top and the bottom. And they sum out to a little bit of net terrestrial release. Doesn't maybe look like it there, but.
So the blue line in the middle is the sum of the two?
Oh, the blue line is a CO2 in the past interglacials.
What about just a summation of the top and bottom diagrams?
Well, the top and the bottom are carbon burial, but the middle plot is CO2. So the middle plot is telling us, the blue line is telling us what CO2 did at the end of previous peak interglaciations, and it went down steadily for all those 10,000 years. And so something was pushing CO2 down, and as I opened the talk, I was showing you that ocean chemists would tell you that's because the carbon was being stored in the deep sea by those two mechanisms that I showed you. I'm saying, as Franzen and his group suggested in 1996, that the peat burial must be playing a role because there's hundreds of billions of tons of carbon apparently going into peat in those previous interglaciations, and so that would explain, or part of the CO2 drop in the previous interglaciations that was not canceled by anthropogenic carbon. So it's another, flip it around. Anthropogenic emissions prevented a glaciation that would have begun by now by some combination of carbon sinking into the deep sea, but also by peat burial. And the conventional explanation has pretty well ignored this peat factor, but I don't see how you can ignore it. Doesn't make sense. Stephanie.
So can you talk a little bit more about the C13 effects of peat burial versus anthropogenic emissions, and whether, because you invoke this argument to explain that small C13 decline more recently. Is that borne out in previous interglacials if you think about the mass balance that you just presented? And what are the details of this C13?
There's some, first off, it's an amazing technological feat to take these tiny air bubbles and then pull out CO2 in parts per million and then pull out C13 of CO2. But there's been a few analyses from the previous interglaciation, and they're not, I don't recall them in detail, but they're not definitive in any way. They're hard to interpret, so I don't think so far it makes a strong argument either way. And the people that have made those analyses, who are among the people who don't like my hypothesis, have not used them to go after my hypothesis.
So is it true, though, that the C13 of the anthropogenic emissions would have to be similar to the, if you only invoke the peat sink, would have to be similar? You have a little more emission than uptake, and it would have to be something like -20.
Yeah,
to get to
the C13 composition of terrestrial carbon coming out of agriculture is minus 25, and the C13 composition of peat burial is a little more negative, minus 26 or minus 27, but it's got a first order the same. So it's that they factor that in, but basically it's the similar billions of tons of carbon that's that is where the cancellation comes. So the observed C13 signal does go more negative, which is consistent with some anthropogenic release, but much, much smaller than I claimed. I think the answer in that particular index is mostly peat burial, but I learned yesterday that there's terrestrial soil carbon considerations, and I know there are other papers that carbon gets buried in river floodplains and in deltas. It gets buried, it gets exhumed, and nobody knows what that signal is. So this is just restricting it to two factors, because we know enough about them to put some constraints, but nobody really knows the constraints of the floodplain burial, and I don't know the carbon in terrestrial soils. I was told yesterday that there are emissions of 140 billion tons, so we have all these uncertainties flying around out there. But I pay attention to the geochemical arguments, but I always come back to, well, carbon dioxide was rising when it should have been falling, and people were doing all this stuff clearing forests, so how is that not the story? Yeah.
Bill, so the rise of CO2 at 6,000 years ago, that rise, if I understand your argument correctly, is in a mass balance sense the net positive that's produced by agricultural activity. And by then, if that's true, then if we didn't have the peat bogs, would we have had a major global warming event starting 7,000 years ago?
We would have had a more substantial warming than we had back then, but it's modest in amplitude and it's very slow. It's spread out over thousands of years. Of course, what we're doing in the last, going from 280 to 400, we've done that in 100 years or 120 years. So it's just completely different rates. I get accused sometimes of being like a climate skeptic or something, because people say, well, look, this comes off of last night's talk. Greenhouse gases are our friend. They stop the glaciation. and no, they kept global climate warmer than it would have been. It would have been just beginning to slip into a glaciation. But what we're doing now is just a whole different thing altogether. And so my data cannot be used to say, or my hypothesis can't be used to say that. Yes?
I'm thinking about this upper curve of billions of tons of carbon in peat and trying to imagine what the next data point is going to be. Because I'm caught up in this idea of permafrost releasing material and sort of even thinking about why it's being buried over the past 5,000 years rather than these, sites of peat storage maybe becoming carbon sources to the atmosphere.
Right. Well, the great thing about the stuff I talk about is the first thing I say is, well, I'm not an expert, and I'm not. But my understanding of forming peat and putting and permafrost and things like that, you need an environment where the summers are warm enough to support vegetation, putting the carbon on the land. And let's see if I get this right. The winters are cold enough to freeze the activity and to do some burying. but not with ice sheets. You don't want to cover them with ice sheets. So you need something that's it's very cold climate, but warm enough to have vegetation burying, forming vegetation and inevitably putting some of the carbon into the soil. My understanding of permafrost, and there are scares about methane releases and things like that. My understanding is the best science says there will be releases of carbon from around the Arctic, but a lot of these billions of tons are buried deep enough that it's very hard to erode them using temperature going downward. If they were being heated from below, you could get rid of them very fast, but you can't do it so easily from above. So there's a break on the system. So I would expect, I guess, that the curve would turn, or maybe it has turned up if they think they know it, would have turned up gently, but not explosively, and that it will continue up as we keep warming, but probably not in the alarmist way that some scientists have suggested. Does that sound right? You're not an expert, so.
Is there a relationship between like these rates of peat formation and thus carbon burial and the orbital forcings that are happening that are also related to starting glaciations? So I guess I'm asking, what's the sequence of events? Do we have to have like orbital forcings that then drive more peat burial, which becomes a feedback? And
I think the basic sequence is that in some of the areas, like North America, you have to get rid of the ice sheet to have a land surface, and that's in Scandinavia. It's not so true in Siberia. The ice sheets aren't extensive. So you have to get rid of the ice sheets, which requires these summer insulation peaks. And the same summer insulation peaks that have gotten rid of the ice sheets then warm the land enough in the summer to permit vegetation to grow, which allows you to sequester carbon in peats, so long as the next ice sheet doesn't come and kill the process. That's about as far as I go, but.
so that also then might explain like then why like in the top plot, for the plot A, that the greatest rates of peat formation are happening when we've got the maximum summer insolation, which seems, at least down at this latitude, seems backwards.
That's probably true. And it's still going on, but not quite as fast. Well, you've got summer insolation is decreasing in the northern hemisphere all the way through those 11,000 years. So mountain glaciers are beginning to have larger and larger maxima. They call it the neo-glacial. I don't know if that's a reasonable term. It's nothing like a glaciation, but it's some mountain glacier advances. And so summer insolation is still a major driver. Even though CO2 is going up, insulation's going down. So those two are competing in the last 7,000 years.
Yes.
In your initial slide, you had 4 oscillations without men, and then the last one with the men. How far back do you run that on back through time before your slide began? Were there oscillations?
How many more cycles back there?
Yeah, back, back through the beginning of the Cretaceous or something.
Oh no, the ice cores go back 800,000 years. So what I showed you was half of what the records we have, and beyond that, there's no ice cores. There's hopes that if they drill in certain parts of the central East Antarctic ice sheet, they might get 1 million years, but that'll be it. And there's no other deposits that you're going to get earlier records or greenhouse gases or any of that.
So you can't measure it, but if you had 60 million years, what do you guess might have been back there?
Well, that's too big a question to get my mind around and sound coherent. Let's see, no ice sheets, no permafrost. That's probably basically right. 60 million, if you pick that, it's very warm. No sea ice in the Arctic, no permafrost, no Greenland ice sheet, no Antarctic ice sheet. Right. Completely different world. Some parts of which we're going to.
Of a glaciation in these peatlands, and I mean the peatlands must be exhumed, right? With the advance of the ice sheet, these boreal peatlands disappear, and so what happens to all the carbon that's stored in those peats?
Yeah, it's. I don't really know the answer to that, but my guess is, well, where there are ice sheets, it gets scraped
Scraped away.
and exposed and eroded, and maybe what would it do? It keeps CO2 from going down more than it actually does, because it's coming back out of the vegetation, but it's going into the deep ocean according to conventional wisdom. So those are the two players I can think of, but I'm just guessing.
Is there a big release? There's not a big release of CO2 associated with glacial
No, but
development.
ice sheets advance in fits and starts in time transgressively from region to region, so you don't need to expect a big spike. It might just be a background tendency to release carbon and offset some of the CO2 decrease that would otherwise occur. But I guess I would need to think more about that subject to make sure I knew what I was saying. Yeah.
This is a great mystery, right? You've got signal to noise issues, and I'm curious if you could comment on methane cloth rates and the role they may play.
On this time scale, 10,000 years.
A little bit longer, like thinking about one of your first slides that looked at several of those sawtooths.
Well, there's a methane cloth rate hypothesis that supposedly, well, that proposed that there would be huge methane releases as the ocean warmed around the Antarctic, and you'd have big releases of methane into the atmosphere, but for various reasons, 2 or 3 of them, none of which quite come to mind, that's not in favor anymore. I think that was Jim Kennett's Clathry gun hypothesis. I guess the first answer is there isn't this concentration of dated clathy releases that would affect the look of the seafloor sediments on these continental margins. So it occurs, but it's not really focused in time. It's the first and major answer. Yes.
Doesn't Jim Hansen propose that typhoon cycles related to interglacial periods drive tropical peat production, and that triggers melt and freezing?
Could you go again? And your voice is soft.
Okay, sorry. I think I'm not very up on all this literature, but Jim Hansen in his Storms of Our Grandchildren,
Yeah.
he talks about typhoon cycles. I believe
Yeah.
it's in that book, and the expansion and contraction of tropical wetlands and their peat and carbon sequestration.
I think the reason he came up with that title, that was a book title, I think, was that there are interglaciations like the one back 120,000 years ago, in which there are deposits, I guess it's of coral reef, blocks of coral reef that are thrown up onto Bermuda and other areas that are just a bit extra tropical, and he's trying to explain why they're up there, and some people say that's because sea level was lots higher, and I think he was thinking that the warmer than modern conditions create massive storms that can lift those blocks up because of storms, but it's not sea level. I think that's the basic argument. If anybody knows different.
I think and I may be confusing that with some other stuff, but I thought part of his multiple arguments, he talks about the
Yeah, that's,
But he talks about typhoons increasing wetlands expansion in the tropical wetlands, which increases peat sequestration, which
Right.
decreases CO2. Which
I don't
cools
remember
them.
his focus on.
But I guess the question I'm trying to get towards is, we talk a lot about boreal conditions, but tropical peat. And then that would relate back to your question, which is now that we're deforesting all the tropics and, you know, keeping the Mississippi River from gaining deltas, and also the same thing in Bangladesh, that we starting to lose these wetlands just from anthropogenic disturbance, which would lose the expansion of those, or maintenance of those wetland conditions.
I couldn't answer it a quick,
Yeah, that's done.
in a hurry, what global wetlands are doing on average. I'm fairly certain they're shrinking for all kinds of anthropogenic reasons, but I'm not quite sure. Pretty sure that's true.
Yeah. Could you talk about some of the mechanisms that would explain that jagged nature of the, after you have rapid warming, you have a slow cooling, but it's not smooth, and
It's like in the CO2 curve.
yeah, what are the mechanisms behind that jagged?
Well, that's still one of the great questions out there. I mean, the whole 100,000-year cycle is still being debated, and different people have different opinions. My opinion is something that comes partly from Maureen Ramo and a little bit from an early Wally Broker paper, which is that there is a natural tendency or bias to cool the climates. Maybe its central state is cooler than normal, and that so you tend to build ice sheets, but you can get these oscillations. You see them particularly clearly around 250 to 200,000 years. Those are 20,000-year cycles, very obviously the orbitally driven structure on top of this 100,000-year sawtooth. But the system tends towards growing glaciers, and glaciers provide their own positive feedback, or I should say ice sheets. But you get to a point sooner or later, and this happened very much around 330, 220, or 40, and 120,000 years ago, that if you get the tilt and the precession cycles, which are different wavelengths, if you get them coming and producing a peak that is nearly coincident, that's like a super pulse that's an extra pulse of forcing to get rid of the high. It gives you high summer insolation, which gets rid of ice sheets. So those rapid deglaciations are orbitally driven, and I think they're because tilt and precession. And if you figure out the tilt and precession cycles when they come in and out of phase, it matches pretty darn well with a rapid deglaciation. So that kicks the system warmer than it normally wants to be, and then the system starts trying to get back to a colder condition. Probably the mean condition somewhere in the middle. But then when you get out large ice sheets, they start driving positive feedbacks that help them get even larger until you get one of these peaks that kicks you out. That might not be the answer you get from everybody. It won't be the answer you get from everybody. I think the truth is something like that. I mean, it's kind of exciting. There's still, that's a big prize out there. And it's people have claimed parts of it, but not the whole deal.
You mentioned the positive reinforcement of periods of glaciation. I know that some of that, maybe all that's due to albedo or reflectivity of those surfaces. Are there other factors in play?
Well, yeah, the ice sheet albedo is one of the two big ones. The other one is there are mechanisms by which ice sheets drive CO2 down. They create coolings that in the internal climate system that are positive feedbacks, and so that drives CO2, even the global temperature farther down than just the ice sheets do. Insulation drives the ice sheets drive some CO2 feedback that enhances their own effects, and I think that's pretty much universal feeling among scientists. Which those feedbacks are is not so clear. I mean, there are things like you create more dust to the ocean, the dust fertilizes the ocean, that that creates more nutrients for photosynthesis, which sends carbon to the seafloor, and things like that. Yeah.
What's next for you in terms of this hypothesis? Are you going to play it out eventually to a publication?
For this idea?
Yeah, right.
I've been taking a sabbatical for a year, and I only work about at peak at 20% of the week, and I've been enjoying my sabbatical for the 20%. I've been catching up on gardening and all kinds, reading and all kinds of things. So I just have to get back in my pajamas and bathrobe and sit in front of the computer and get busy. So I think I've got another year or two of writing or what have you. But I've really come away from the years of fighting with the geochemists and all that. I'm just content to sit back and watch the people who are doing these wonderful land use studies, pollen and archaeology. The ground truth evidence is just so good, and it's not going to stop. So just sit back. I don't do that kind of work, so I monitor it. But this is the only thing I've had that's, other than figuring out details of a hypothesis to fight back against critics. This is the only thing like a new idea, but it almost seems embarrassingly simple, so I need to persuade myself it has enough merit to get it submitted and get slaughtered in the first reviews. Get my ego back out of the trash can and keep going. It's not as important as it used to be. That's sounding really retired.
So following up on that, for graduate students, based on your long career, what would you have to say to a graduate student by way of advice relative to conducting research? Kind of the biggest message you could send them.
I would have several pieces. One would be get into the best place you can get into after looking around what places offer. Try and identify a really good, decent advisor, and especially an advisor who is smart enough to pick to listen to what you want to do and to get you started on some problem that's related to it, and then is smart enough to just stand back and let you go. That worked for me.
These students have already done that.
So it's sort of common sense, personal stuff. Nothing dramatic. Lots of questions. Thank you. One more.
Kind of along those same lines, what advice would you have for maybe undergraduates who are environmental scientists and going out into a world where maybe political powers that be are devaluing the work that we do?
That's an easy question. I've always known people who are so filled up with their own wisdom that they'll give advice that relate to something they learned 30 years ago, and I don't know enough about what's going on to give a good answer to give really good advice to a student like that, other than it's an interesting field, and if you like it or love it, go ahead and go into it. But gives recognizing that you that you love the work, also think a little bit about what jobs are like at the other end and what the lifestyle of a person who has to get research funding is like. And it's a world I don't know anymore. I had it so easy. That's so my advice is irrelevant.
Right.
Thanks.
Thank you. That's